Hi, my name is Tamar Zondiner, and I'm a backend developer at Waze. I joined Google about 8 years ago as a junior software engineer right after completing my master's. It was my first programming job. I didn't have any experience from the army or anything, and I had a lot to learn. Since joining Google, I worked on several different projects with different development stacks before arriving at my current role on Waze's routing team. Waze routing is an amazing project because we get to focus on this one huge, never-ending challenge of improving navigation worldwide. We get to experience our impact every time we get behind the wheel or hear complaints from our friends, family, or taxi drivers. And we are constantly challenged to improve our routes and save people precious time. But when it comes down to it, we basically compute shortest paths on a graph. A lot of the success comes from having a good informed graph. Wazes Graph, the map, is created by Waze's wonderful community of editors. Its edge weights are created from historic and real-time speed measurements gathered from our drivers. Using this graph, we get a query from a user and essentially compute a shortest path search. The basis is very simple, and you probably know it if you remember algorithms like Dijkstra or A-star search from school. So how come we've had people working on it for over a decade? What have we been working on for so long? Well, one part of it, of course, is scale and speed. This is a very heavy computation. Also, Waze has a lot of users, and when a user is driving with the Waze app, their route gets verified and recomputed every couple of minutes, and that's a lot of work for our servers, so we want our computation to be efficient. Another issue is that our users need a bit more than just the shortest path. Speed isn't everything, and we need to balance speed against the simplicity, smoothness, and just sanity of the route. We do this by adjusting the weights to penalize bad route patterns, like taking a driver off and back on a highway just to shave off a few seconds. Of course, to find such patterns, the algorithm needs to look at the route more holistically and not look just on simple edge weights. So that's already more than just a textbook Dijkstra search. We also want to return more than just one route. We want to give our users options, and that's something even less well-defined. The thing is that the theoretical second fastest route is very likely to be a route that's almost identical to the fastest route, with just one turn taken differently or some small deviation. It's not really an interesting alternative to show a driver. We want an alternative that's substantially different. Intuitively, in a conversation, you'd expect something like, should I take route 4 or route 2? Most likely, we want to change the route in its middle, its core. So how do we get that? One algorithm that we use is a variation on bidirectional A-star. Usually, it's used to compute just one shortest path between 2 points by traversing forward from the source and backward from the target and meeting in the middle. Let's follow this traversal. When the 2 traversals meet, that is the shortest route. Now, what happens if you save this shortest route, but then keep traversing? Then you will find more meeting places of the forward and backward traversals, which form more routes. Now, some of these routes are still going to be small variations of one another, but if you keep searching, others would be substantially different. From those routes that we collect, we pick the best 3 diverse routes to display. At this point, we can also take into account properties of the routes, like toll costs, to make the variety meaningful. Overall, we do a lot of things, from tweaking and mending to adding new features like high occupancy vehicle roads and toll prices, to exploring new efficient algorithms on graphs. We have an interesting problem with a lot of impact, and our work is not nearly done. Thank you for listening.